Good afternoon, everyone. My name is Dharmendra Kumar Singh. I am a postdoctoral associate at the University of Illinois, Urbana-Champaign. Today, I am going to present the impact of aviation contrails on the global environment using the SSP2-4.5 scenario for projection. So, SSP stands for the shared socio pathway and shared socioeconomic path. One second, I think I can do this. Yeah, I'm audible. Okay. So, yeah. So 4.5 is the watt per meter square. That will be projected for the 21st 100 by the end of the century. So contrail is the line-shaped cloud, and that is generated by aircraft emissions and how it mixed to the based on the temperature and humidity. So why contrail? So why study contrails? So aviation growing climate impact, contrail serious key uncertainty in radiative forcing, and how do contrail form? So mainly it forms depend on the atmospheric temperature and humidity. And if too dry and too warm, so there is no contrail formation in this graph here. You can see, and too humid and cold, more serious formation takes place. Because of that cirrus, there is very difficult to and challenging to distinguish from the contrail from the natural cloud. So the main challenge of contrail to distinguish the contrails from linear contrail from the contrail cirrus. That is the natural contrail. So normally linear contrails identification that form the time scale up to an hour or so. In our model is 30 minutes. And from contrail cirrus, it is 1 to 12 hours. And hard to distinguish from the natural clouds. Here you can see how linear contrail that can be detected by the satellite, and contrail cirrus is when it overlap. That is another challenge to distinguish from the natural cirrus. So this is the data set from global aviation effective radiative forcing, and it is calculated by the Lee et al. 2021. This mainly shows how much the contribution of contrail from the non-CO2 to CO2 level. So overall, if you can see the net all aviation, all terms, only 2/3 part of the non-CO2 parts, and out of that non-CO2 parts, contrail forms 86% of the non-CO2 impact and 57% of the total aviation climate impact. Here you can see this is 57 milliwatt per meter square, the effective radiative forcing. If you compare from this net aviation, it is 57%, and here all non-CO2 terms combined account for the 2/3 of aviation contrail climate effects. The objective of this study is first to project the global radiative effect for 2035, and second is to quantify the regional variations, and in the third one, the assesses the implications for sustainability. So we use the CSM CAM6 climate model of NCAR, that is 1 degree grid, and 10-member study was chosen. And SSP2-4.5, as I said, this the shared socioeconomic pathway at 4.5 for the how much radiative forcing by the end of this century. And FAA, this is the data set we received from the Federal Administration Aviation Aircraft, you can say, yeah, aircraft emission data tools, emission 2035, and it was scaled. A robust statistical analysis was performed. So model framework ensemble approach for robust projections, this 1 degree 10-member ensemble was taken for the understanding the how much variability, especially natural variability, by putting the initial temperature here. So why initial temperature is important to put in the simulation? Because it ensembles quantify uncertainty, contain radiative forcing, critical for actionable, sustainable strategy. So it gives mainly the natural variability in the simulation. So let me walk you to the next slide for results and discussion. So here we can see seasonal mean distribution of aircraft water vapor mixing ratio is water vapor for different seasons, and it was observed that the mixing ratio, that is kg per second, it was highly concentrated in the part of the North Atlantic here, and North America, of course, land area, and Western Europe here and here. This is the water vapor emitted from the aircraft. So it was calculated by using for the model purpose, so that you can use in the model in the mixing ratio. And the second part of the result is ensemble mean of radiative forcing of milliwatt per meter square at the top of the atmosphere. So it was found that around 130 with 225 standard deviation was recorded of 10 ensemble members with normal distribution with 95% confidence interval. Similarly, we found the cloud radiative effects. Cloud radiative effect is the summation of the short wave and long wave cloud forcing. So it was found that 156 milliwatt per meter square was recorded with a normal distribution of 95% confidence interval, all the 10 ensemble members. And this is a busy slide, but it gives more information about seasonal variation of radiative forcing at the top of the atmosphere for 2035. So the red regions indicates the warming effect, while all the blue indicates the negative cooling effect. So high RF, deep red are seen over the major corridors, especially the North America, where the water concentration was high. Similar, the RF value was found high, that is the North Atlantic and North America, Western Europe, and part of the East Asia. Yeah. So the warming effect is generally strongest in the December, January, February, in the winter and autumn. Here and here you can see the diagonally. So this is the winter, and this is the autumn. September, October, November is autumn here, and the same region show the cooling, particularly in the summer here, June, July, and August here, and over certain oceanic and higher latitude area. So the next slide is for actually this picture shows the ensemble mean of surface temperature in Kelvin, and each ensemble member's global mean was found in 0.09 with the standard deviation 0.067, and model this surface tensor was mainly generated by the radiative forcing of that specific contrail. So model temperature response is consistent with expected climate sensitivity, that is 0.5 to 0.8 Kelvin per radiative forcing, that is watt per meter square, supporting the reliability of the results. This is a formula for the climate sensitivity. So the range of implies temperature response of approximately this after calculation from this value of 131 milliwatt per meter square in my result, which align well with the model outcomes at the top of the atmosphere. So this is the seasonal variation and special variation for the surface temperature, and it was found that especially over land and during summer and autumn, high temperature was recorded. High temperature in the sense here warming signal in respect to that value. So there is a seasonal pattern. Warming is more widespread and intense in June, July, and August, in summer and in autumn. Some cooling was also recorded in some parts of the North America and Eurasia. So the key findings, I would like to go briefly here. The key findings for this study was the radiative forcing at the top of the model. And it was found that contrails are significant contributor to the Earth's radiative budget, and the same model of NCAR CAM6. And this is the present study of 131 milliwatt per meter square. And in our previous study, with the same model and with same method, it was found 52.5 in 2006, and 60 2018, and 90 2019. And after that, my simulation is going on for the current year of data. So there are some issue in the Derecho computer, supercomputer of NCAR. So I'm waiting the result for the 2024 for current study. And the projection study for SSP2-4.5 was found 131, 130 you can say. So here, yeah. Yes. So future work, I would like to say the I guide is really very important for my research for future study. Here we can see how machine learning and geospatial AI is important for contrail prediction mitigation, and that can use the modern deep learning models, and that feeds the geospatial integration, high resolution atmospheric data, open source platform, and that policy and mitigation uses the data and work of the machine learning and AI, and these all efforts can be useful for the sustainability. So geospatial integration of our guide leverage the geospatial AI tool to analyze the visualize and high resolution atmospheric data, flights, trajectories, and contrail hotspots. So develop open source platform to sharing contrail prediction model and data, fostering innovation and collaborating with the iGuide community, enhance data assimilation by integrating aircraft sensor data, satellite observation, and advanced weather models to improve forecast accuracy. So here you can see these all 4 pillars are very important for future work that can, especially for the mitigation of the contrail. So AI for the accurate contrail prediction, and second, ensure our data to actionable and widely accessible for geospatial integration, and for policy and mitigation, turn our findings into real world action. And sustainability, of course, supports the sustainable aviation practices. So these are the references, the main references for this study. Thank you.
Great, thank you very much. So that was very interesting.
Yeah.
So does anyone have any questions for Dharmendra? We have a few minutes. Yeah, Carol? Yeah. Do you need the microphone? Okay. Okay.
So I'm just curious, in the big scheme of things, like how do I say it? So what's the impact of Contrails compared to other things?
Really, this is the. Yeah, I understand. Yeah, actually, contrail is really very complex topic. So for understanding contrail, we need to understand the effective radiative forcing, because effective radiative forcing, we know radiative forcing, the short wave radiation and long wave radiation, the balance of the short and long radiation at the top of the model, that can cause the warming. So we need to understand how much surface temperature can be generated by those radiative forcing. But radiative forcing is not only single parameter. For that, we need to go to what is effective radiative forcing. How much natural clouds are responsible to increase the radiative forcing or decrease the radiative forcing. So in that case, once you understand the effective radiative forcing and short wave, long wave radiation, you can understand what the future global warming, especially climate change point of view. So mainly it is a cloud and aerosol interaction. So here I did not include the aerosol, because aerosol causes the very much uncertainty. That's why I just excluded the aerosol. and I used the water vapor from the aircraft. So those water vapor aircraft as a mixing ratio was used to understand the how much contrail can provide the radiative forcing, and because of that RF, how much surface temperature can be generated. So for that, we need to understand many other parameters. I use only one parameterization using CAM6 model of NCAR. So also you can put the aerosols, and so that you can understand more how much other cloud parts can be impactful for this calculation and simulation.
So, question. So, I'm trying to understand like computing resources, data resources. How
Yeah.
Are there things that would really get you to the next level?
So the data set was observed, measured by the aircraft in 2006. We got this data from the FAA, Federal Administration Aviation. So those data after 2006, you can say it's been around 20 years. So we don't have the data after that of whole data for global coverage. So those data we are using for scaling method. So what I used, I couldn't explain because it's 15 minutes here. So this is a good question. So if we are going to use the 2006 data set for that RF in that particular year, so it was found for some model 50 milliwatt per meter square. When it was scaled by Lee et al. From 2006 to 2018, they used the growth of the aircraft, how much travel, and then they got some value, the 1.58, the ratio of the distance traveled at that particular year to 2018. Then what I did, I used the 9% growth factor that was reported in the previous studies that was published, and that 9% growth factor was used to multiply from 2018 to 2035. So these data is input data of water is for multiplied by 9% of growth, and that was the data set. And the CAM6 model was run by the supercomputer of Derecho and Cheyenne. Now initially it was Cheyenne, but now it's Derecho of NCAR NSF.
Great, thank you very much. Maybe, are there any other questions? Okay, well, we're running pretty much perfectly to time, so thank you very much again.